Hey everyone, hope you're doing well. This is going to be Lab 3 Magnetic Field of a Bar Magnet. The purpose of this lab is to explore the relation between magnetic field and distance, both on and off axis. We'll compare the distance that we got from the measurements to the one that we can get from VO using glow script. And we'll also model the magnetic field of a dipole and find the dipole moment using experimental data. First, we'll go over the physics fundamentals, then the calculations, and then the models we produced, and finally we'll end with a discussion. The main result of this lab was that field strength increases as distance decreases. So a magnetic field is the region around magnetic material or moving electric charge where there is a magnetic force. And for Biot-Savart law, here we have three versions. The first is the magnitude of a magnetic field on axis given by mu naught over 4 pi times 2 mu over r cubed. Then we have the magnitude of the magnetic field of a bar magnet as kr to the n, where n is the distance dependence value. And then we'll later take the natural log of this equation so that we can plot it in the mx plus b form. And then this last equation here will be used in the glow script model to visualize the magnetic field. And there's some assumptions that we need to make, that only r is not a constant, and that we are going to assume that n is expected to equal -3. To estimate r from our data, we generated a logarithmic plot using the measured distances as seen here. We can do this by using the condition that the equation for the magnitude of b bar can be transformed into this logarithmic equation, and this is in the form of y is equal to b plus mx. Now we find the linear regression equation to be y equals -3.0823x minus 14.533. Using this equation, we can now find n, k, and the dipole moment mu. In this equation, n is just the slope of the regression, so n is going to be equal to -3.08. This isn't too far off from our expected value of -3, so that's good. Then to find k, we can set x and y to the origin so that ln of k is equal to -14.533. Then with some calculations, we find that k is equal to 4.88 times 10 to the -7th. Finally, to find the magnitude of the dipole moment, we can assume that the magnitude of the bar magnetic field and the dipole and axis magnetic field are the same. So as you can see here, we set these equations equal to each other and find that mu is equal to 2.43 am squared. In the second part of the experiment, to measure the off-axis magnetic field, we positioned the magnetometer a distance d perp in the x and y direction using the magnetometer app. We found an average d perp to be 0.17 meters and the average magnitude of the net magnetic field to be 1.8 times 10 to the -4 Tesla. Now, in order to compare measured B-net results to a predicted model that uses Biot-Savart, we can use glow script and input the average d perp we found before. As you can see, we have a pretty big difference between the measured and predicted magnetic field values. Now let's model the actual magnetic field using glow script. Here's a part of my code, and if you want to see more, click the link in the description box below. This is what we got, and notice that the on-axis vectors in orange are twice the magnitude and opposite in direction than the vectors perpendicular to the magnetic dipole moment. To conclude this experiment, we'll end with a discussion. What if we hadn't oriented the setup to compensate for magnetic north? Well, in that case, the magnetometer readings would be skewed in the direction of magnetic north, and the results of the values of k, mu, and n wouldn't be as accurate. And then what if we stuck two magnets together end to end? Here, the direction of the magnetic field would still remain the same, flow in the same direction, but the magnetic field's magnitude would double, so it would be twice as strong. That was all for this lab. See y'all next time.